Okay, hello everyone, and welcome to our final live stream of the semester. This is going to be a live stream on the first law of thermo. And, it's kind of nice actually that the class ends with thermo because if you do it right, it's pretty easy to get a lot of points with thermo. It's not that bad. Now I say this, but there's a caveat in a sense because throughout the entire class we've emphasized time and again that just knowing formulas and trying to blindly apply them is effectively shooting yourself in the foot and is possibly one of the worst ways of basically not knowing how to solve problems in physics and guaranteeing that you won't do well on a test. And having hammered that for, almost 15 weeks, now I stand here rather, and I'm about to say that what you should do for thermo is blindly apply formulas on the condition that you know exactly which formula applies when. So there's no messing around with words. Now in general this is true in physics, but it's particularly true in thermo. None of this nonsense of, oh, it's isothermal, so temperature doesn't change, which means that Q has to be 0. Bullshit. Isothermal means constant temperature. Adiabatic means Q equals 0. And you don't start trying to interpret or think about what it means to have constant temperature and whether or not heat can be transferred. So it's very hard to think about thermo conceptually and do it properly. You can think about thermo conceptually, but half the time students get it wrong because it's really hard to tie everything together and not make a mistake just because of the nature of thermo. So then it turns out that yes, the best way to do thermo in terms of maximizing the number of points that you can get while minimizing the effort that you put into thermo is in fact to know which formula applies in which case and to just run with that. You just, you know what, we're going to apply blindly the formulas. And you want me to compute work by for an adiabatic expansion? There you go. This is the formula. Done. So I don't encourage that. I don't truly believe that at heart because I think the best way to do thermo is to truly understand it and to be able to think through problems. But the truth of the matter is, this is the last chapter. Usually we're running late. The final is in 10 days. And if you want to maximize your points, you have to just know which formulas to apply them and trust the math and just, however, be very careful what words mean. And don't attribute to words meaning that they don't have in general, but particularly in thermo. Okay, so I'm done with my little rant, but that was a disclaimer because everything else we've said up until this point has been the opposite. And so in light of what I just said, I'm not going to try to rederive things or like present thermo through an understandable angle and all that. We're just going to make two tables. One table of monatomic, diatomic gases, Cp, Cv, gamma, boom, and one table with Q, work, delta E, and the 4 processes that you need to know. And those are your formulas, and that's what you use to solve problems. Okay. Now we are going to very briefly recap the first law of thermo and an important property of internal energy. Now the first law of thermodynamics, the idea is that there is an energy called internal energy, which is the sum of all the microscopic sources of energy that we've never accounted for before. Chemical energy and nuclear energy and whatever else you want, thermal energy. And for sake of simplicity in this class, internal energy can be thought of as thermal energy. Okay? And the first law of thermodynamics is a statement of change. It tells you, should you undergo this transformation, this is what the change in internal energy is going to be. It doesn't say whether it's physically possible to undergo the transformation. It doesn't really care. It just says, what do you want to do? Oh, this? Okay, here is delta E internal. And in all cases, it's going to be Q on, which is going to be the heat transferred to the gas, which by the way in our case will be an ideal gas, minus work by, which will be the work done by the ideal gas, and by definition is equal to the integral of P dV from V initial to V final, the initial volume to the final volume. A few things. First off, you might have seen Q on plus work on when it comes to the first law. You might have seen that before. It's the same thing, of course, because work on is minus work by Newton's third law. But this is usually what you use in chemistry. It makes more sense to do Q on plus work on in chemistry. But in physics, we will use Q on minus work by, meaning that any formula I give you here is work done by the gas, not work done on the gas. If you want to answer a question that says, well, what is the work done on the gas, from 1 to 2 or whatever, it's like that, I'm going to find the work done by the gas, I'm going to put a minus in front of it, and that's your answer. That's the work done on the gas. Okay? So just to clarify that. Second, internal energy is a state function. What is a state function? You could argue we don't really care, but I'll tell you anyway. A state function is a function whose value is only a function of the thermodynamic state of your gas, meaning that all internal energy cares about is where you start and where you end. It doesn't care how you went from the initial state to the final state. Just doesn't care. And so delta E internal, as it turns out, we're not going to prove this, but we're going to accept it, that for any process that you can encounter will always be NCV delta T. And we're going to define CV in a second. But that's something important to keep in mind, because if you want to find delta E internal, you can always argue that it's NCV delta T. But you can also always argue that it's Q on minus work by. And therefore, if you were to compute Q on and subtract work by, you would actually also find this. It all is coherent and it ties, right? But those are two important things that we need to talk about before we go through and do the following summary. Okay, so the first part of the summary is going to be the following table. It is going to be a table that has specific heats in gamma, and then 2 columns, monatomic and diatomic. Okay, so monatomic gas and diatomic gas. Okay, just to be clear, monatomic gases have one element, right? So it has to be a noble gas. Helium, argon, one of those guys. Diatomic, 2 atoms, right? So N2, H2, O2, and so on and so forth, right? So the air that surrounds us overwhelmingly is diatomic, right? Yes, I know CO2 is not diatomic, but if you, for simplicity's sake, the air that surrounds us is diatomic. Okay, so then we need then to have one row that's going to be Cp. That is going to be the specific heat at constant pressure. Cv is the specific heat at constant volume. And gamma, by definition, is Cp over Cv. And what does gamma measure? Doesn't matter. Nothing. In fact, it measures how much bigger Cp is relative to Cv. That's it. It's just a ratio. Okay. And we're going to fill this out. And this is an important table because typically problems tend to tell you whether you're dealing with a diatomic or a monatomic gas. And in so doing, they're giving you this information. In other words, it is fine to say, oh, well, if you tell me it's monatomic, I know Cp, Cv, and gamma. It's expected that you would know them. So what is going to be Cp? Cp, first of all, just as a reminder, Cp is the specific heat at constant pressure versus Cv is the specific heat at constant volume. Right? It turns out that when you heat a gas, it matters. Its ability to absorb heat depends on whether you heat it at constant pressure or at constant volume, and you get 2 different values. But Cp for a monatomic gas is going to be 5/2 of R, while Cv is going to be 3/2 of R. And then gamma, which is Cp over Cv, is therefore going to be 5/3, which is approximately 1.67. Everybody's pretty happy with that rounded value. Diatomic gas is going to be Cp is 7/2 of R, Cv is 5/2 of R, and gamma is going to be therefore 7/5, which is exactly 1.4. And Cp is always bigger than Cv. Okay, so if the problem tells you that you have a monatomic gas, you get to argue that you know all this. If it tells you have a diatomic gas, you get to argue that you know all of this. Okay? So that's the first table. Next table is the following. It is a table where we're going to list the 4 fundamental processes that you need to know. And then we're going to list the formula to compute Q on, work by, and delta E internal. Okay, so Q on work by and delta E internal. Okay. So what are the 4 processes? Well, we'll go, there's no particular order, but we'll start with isochoric. Isochoric or isovolumetric is constant volume. Then there's going to be isobaric, which is constant pressure. Isothermal, which is constant temperature. And then there's going to be adiabatic. And adiabatic means that there's no heat transfer. Q is 0. Okay, so let's be very clear. It is extremely important that we not attribute to words meaning that they do not have, right? So the number of times, now constant V, constant P, I mean isochoric, isobaric, nobody fucks those up because it's almost impossible. It's like, okay, well, it's constant pressure and constant volume. The trouble starts with isothermal. Isothermal means constant temperature. It does not mean, it will never mean, no heat is being exchanged. And the number of times I've read that is just not funny. Okay, so isothermal only allows you to claim that temperature did not change. It by no means implies that there's no heat transferred. Turns out there can be heat transferred, there probably is, it's just equal to the work done. And so it washes out and you get delta E is going to be 0, however, not Q. And adiabatic, of course, is Q is equal to 0. And there's 2 ways to make sure that a process is adiabatic. You can have the process occur in a thermally insulated container, thermos or whichever, in which case you're just preventing heat from flowing by virtue of putting it in an insulated container. That's usually not what happens. Or what typically happens is that the transformation happens so quickly that there is no time for heat to transfer. It takes a long time for heat transfer. It takes 20 minutes to cook cupcakes, okay, just to be clear. Like you put cupcakes in an oven, you get 20 minutes. Don't quote me, I'm not a baker, but you get my point. Like something that's smaller than your fist is going to take 20 minutes to bake. So it takes a really long time for heat to transfer. And if a process happens very quickly, you can argue it's happened so fast that there was no heat transfer. You could very quickly compress a piston, right, in a cylinder. And if you do it quick enough, you just say Q is 0. It's adiabatic. Now after, there probably is going to be heat transfer. There's going to be another transformation. So I'm not saying Q is 0 all the time, but I'm saying, okay, if something happens very quickly, typically that's a buzzword for adiabatic. But very often you're also directly told if something is adiabatic. So just a small side note there. Okay, so let's start with the easy ones. Q will be 0 by definition when I have an adiabatic process. So this is 0. Work will be 0 when the volume of the gas doesn't change. Okay, gas is going to do work. The work done by the gas is positive when the gas expands and pushes on its surroundings. On the other hand, if the surroundings compress the gas because you're compressing it with a piston in a cylinder, then work is being done on the gas. But in both cases, there's work if the volume changes. But if the volume does not change, then the work done by the gas is 0. And the internal energy is only a function of temperature when it comes to an ideal gas. Therefore, if the temperature of your ideal gas does not change, the internal energy does not change either. So those are the easy ones. Then let's do the Q column. For an isochoric transformation, by definition, constant volume means that we're going to use CV, the specific heat at constant volume, and we're going to find that Q on is N CV delta T. And you pick the right CV depending on whether you have diatomic or monatomic gas. Isobaric, similar, constant pressure. Okay, I'm going to use specific heat at constant pressure. So I'm going to have N CP delta T instead. This is where it gets tricky. Constant temperature, you're like, oh, delta T is 0, so this is 0. And then I have to hunt you down and find you. So constant temperature tells you that delta E internal is 0. And just as a reminder, we'll put it here because we might need it again. The first law tells you that delta E internal is Q on minus work by. So all that you can say here is that Q on is going to be equal to work by. We're going to see what that is right here. Okay? Okay, the work by column. Isochoric means no work. That's done. Constant pressure. If pressure is constant, work is simply equal to P times delta V, the change in volume. V final minus V initial. If the temperature is constant, the work done by the gas, and I'm not going to do the derivation, we're just going to write it like this. It's going to be NR T initial or T final. It doesn't matter, they're the same because it's isothermal. Natural log of V final over V initial. And adiabatic, well, okay, if Q is equal to 0, then work by is minus delta E internal. And what we said before is delta E internal is always NCV delta T. So minus delta E internal is minus NCV delta T. And so, final column, delta E internal here is going to be equal to NCV delta T. Remember, it's this column minus this column. Okay, well, that's all consistent, right? This minus 0 is this. It also ties with the fact that delta E internal is always NCV delta T. Delta E internal here, for this cell right here, well, now you could say, well, it's going to be NCV delta T, isn't it, the whole time, that it's always equal to that. It's like, oh, I agree. It's, you know, obviously it's also going to be NCP delta T minus P delta V. Now, if you were to plug the ideal gas into that, it would simplify into this. So we're writing NCV delta T anyway. It's the same thing. It's going to be 0 for an isothermal process. And then for an adiabatic process, well, it's going to be minus work by. So it's just going to be NCV delta T, which is this minus this. Okay. So I would strongly recommend that, well, you do a lot of thermal problems because it doesn't take that long to be pretty good at thermo, but you can do thermal problems using this thing. And, you know, just put it next to it and you'll see how fast you can fly through a thermal problem if you know this, which means you memorize the crap out of it because that's the best way for you to solve thermal problems. And I'm not trying to be demeaning or condescending by saying that you can't understand thermo conceptually, and it's not true. if you want to try, by all means, good for you. But the truth of the matter is, I've done this too long to be talked out of this tree. Usually students are just they're not that good at thinking of thermoconceptually, and the alternative is if they just use the formula, they do great. And I'm more interested in you doing great on the problem than, being a really good conceptual thinker of thermodynamics. Okay, you can always do that over Christmas break if you're bored, but let's right now focus on maximizing the points on the final. Okay, so let's go do some problems. I'm going to do two types of problems. The first one is not that common. It shows up now and then, but more likely than not, you're going to get the second type of problem I'm going to do, which is a cycle. But just to get ourselves warmed up and start using these equations and see what we might be asked to solve for, let's do this first problem where we just take a gas and we're going to extremely quickly compress it from 300 cubic centimeters to 30 cubic centimeters. And it is air mixed with gasoline vapor that enters a cylinder of a combustion engine. And we know the pressure and we know the temperature. And we want to find the pressure and the temperature after the gas is compressed. We want to see how much work is done on the gas during the compression. And then we want to show the process in a PV diagram. Okay. All right, so first things first. If you tell me that I have air as my gas, then I know that I have a diatomic ideal gas. In other words, I know that Cp is 7/2 of R, Cv is 5/2 of R, and gamma is 1.4. So that is just given. I know that. Okay. Then, what else do I know? Well, I know that I start with the pressure P0 is 1 atm, a temperature T0, which is 20 degrees, and a volume V0, which is 300 cubic centimeters. And then after a very quick compression, or an extremely quick compression, I get P1, V1, and T1. So I get P1 to be determined, T1 to be determined, and I know V1 is 30 cubic centimeters. Okay, if the transformation, well, first let's back up a bit. I can only find P1, T1, and V1 if you tell me what kind of transformation I'm looking at. Is it constant pressure? Probably not. Is it constant volume? Certainly not. Is it constant temperature? Yeah, I don't know, or it could be adiabatic. But if you tell me that it's an extremely quick compression, that tells me that it's adiabatic. So this is Q is equal to 0. Okay. So that's one of the reasons I wanted to do this problem, just to re-emphasize that extremely quickly means adiabatic, typically in the world of thermo, and also to use the Laplace formula that we haven't talked about before and that we're going to see here. Before we do that, though, this is also why I want to do this problem, we need to fix these units because they're all the wrong units. Okay, pressure should be in Pascal, temperature has to be in Kelvin, and volume has to be in cubic meters. So 1 atm, unless I'm told otherwise, is pretty much 10 to the 5 Pascal. Everybody's going to be okay with that. Right? It's 1.01325, but unless you actually tell me that, I'm just going to assume 10 to the 5 Pascal. 20 degrees Celsius. Celsius is the wrong unit. I need Kelvin. I have to add 273, which is going to give me 293 Kelvin. Okay, or in theory you add 273.15, but okay, add 273, you get 293 Kelvin. And cubic centimeters, that's going to be 300 cubic centimeters is going to be 300 10 to the negative 6 cubic meters. Okay, not 10 to negative 2, 10 to negative 6. 1 cubic centimeters is 10 to the negative 6 cubic meters. Okay, And then, well, let's go find P1 and T1. Okay, so first things first. I have an adiabatic process, which means that I get to say that PV to the gamma is constant. In other words, P0 V0 to the power gamma is equal to P1 V1 to the power gamma. And that's because I have an adiabatic process. Okay, so that's an important formula to know. I would add that to the cheat sheet, just if you don't already know it. Okay, so then P1 is equal to, well, really V0 over V1 to the power gamma times P0. Okay, now I actually have a ratio here of volumes, so it's going to be 300 over 30, and I could convert, but I'm going to get, what am I going to get? I'm going to get 10 to negative 6 up here, 10 to negative 6 down there. It's not going to matter if I have a ratio. So I don't bother converting to the power gamma, which is 1.4. However, okay, P1 has to be 10 to the 5 because I need Pascal, and then, or rather P0 has to be 10 to the 5 so that P1 is in Pascal. That is 25.1 10 to the 5 Pascal. Arguably 25.1 ATM, but I'm going to give the answer in Pascal because if I need it later, I'd like it to already have the right units. Okay, so I found P1, and anytime I have 2 out of 3 of these thermodynamic variables, of these state variables, PV and T, I can typically find the third with the ideal gas law. Now you're going to say, well, don't you need to know the number of moles of air to do that? And it's like, well, no, in theory, yes, but I can always claim that initially I have P0 V0 over T0 is equal to N times R. That's the ideal gas law before the compression. Well, the number of moles of air doesn't change. So NR stays the same, and this is going to be equal to P1 V1 over T1. Okay, so if I want to find T1, I'm going to say that it's P1 V1 over P0 V0 times T0. All right, so T1 is going to be, P1 is 25.1 10 to the 5. V1 is 30. Now, arguably should be 10 to negative 6, but again, I have a ratio here, so the conversion factor is going to go away. P0 is 10 to the 5, and then this is 300. Multiplied by, careful, I need T in Kelvin, 293. And that's going to be approximately 748.6 Kelvin. All right, so this is 748.6 Kelvin. Okay, so I found P1 and T1, and now I know everything about the final state of my gas. Okay, how much work is done on the gas during the compression? Okay, now careful. All the formulas we have are work done by the gas. So if you want me to tell you what the work done on the gas is, fine, I'm just going to compute minus work done by the gas. That's Newton's third law. And then I'm fine because for work by, I can use the formula that is referenced above. Now, what do I have? I have an adiabatic transformation. So we said that the work done by the gas, in the case of an adiabatic transformation, is minus N CV delta T. So this is N CV delta T. And I know what CV is because it's a diatomic gas, so it's 5/2 of nR, and then delta T is, of course, T1 minus T0. Now you might say, well, okay, now you really need the number of moles. Like, how are you going to figure this one out? Okay, this is a classic trick. Expect that you would have to do something like this in a problem, or at least that it's fair game. Let's absorb nR into the parentheses, and then let's argue that the ideal gas law does indeed apply, which of course it does. 5/2 of nRT1 is just P1V1 minus nRT2, nRT0, I'm sorry, is P0V0. Okay, so this is going to be 5/2. P1 is 25.1, 10 to the 5. V1 is 30, 10 to negative 6, minus 10 to the 5 multiplied by 300 times 10 to the 6. And that's going to be approximately 113.4 joules. Now, does this make sense? Well, let's see. The work done by the gas is positive in the case of an expansion. This is not an expansion, it is a compression. So the work done by the gas should be negative. Therefore, if the work done on the gas is positive, that seems to make sense. Like, maybe I still made a numerical error, but at least I didn't find a negative number. If I do, in this case, there's a chance that I'm computing work by instead of work on. Okay, and then finally, plot this thing in a PV diagram. Okay, easy enough. This is a PV diagram. And we're going to start out at, this is not to scale by any means. Okay, we're going to start out at V0 is 300 cubic centimeters, and then V1 here is going to be 30 cubic centimeters. And of course, we're going to, have a pressure P0 that starts here pretty low, and then it's going to rise pretty high to P1. And now I know that isotherms and adiabats look alike. Adiabats are steeper though. And it kind of makes sense because, let me draw some isotherms here. So, okay, hold on. There we go. Okay, they're not perfect, but they're going to look something like this. All right, so an isotherm is going to look like pretty much a 1 over x curve. Right, so I'm giving an extremely simplified version of it because, again, this drawing is not to scale, but the idea is that this is going to be the T0 is equal to 293 Kelvin isotherm, and this is going to be the T1 is 748.6 or whatever it is we found, 0.6 Kelvin, there we go, isotherm. Okay, and so isotherms kind of look like this, and as you increase in this direction, temperature goes up because temperature is proportional to PV through the ideal gas. So as P and V get greater, temperature goes up like this toward the northeast. And so this would be an isotherm, right? That's why I wrote temperature here is fixed to 748.6, same thing for this guy. And what I know is that an adiabat or an adiabatic process has a curve that is steeper than isotherms, which is the case. It's going to look something like this. Could do better than that. Hold on. There we go. It's going to look something like this. And it's a compression, so we go from right to left. This is your adiabatic process, so this is an adiabat. And it is indeed steeper than isotherms. That's why it cuts across the isotherms like that. Okay, so that's the first problem. Not completely improbable that you might get something like this, although when we give you problems on exams, we tend to prefer problems that involve cycles just because I can write a cycle problem while I brush my teeth. I mean, I'll just give you a cycle and say, all right, go find this, this, and that, and it's going to test most, if not all, of the formulas you need to know, and I pretty much, it's very easy to write one. So more likely than not, you will get a problem that might look like this one. Now, I chose to be a little bit mean here and to have a problem where we have to draw the cycle, but a lot of times the cycle will actually even be drawn for you. So that's even nicer. But let's just see what happens if it isn't and how you can draw the cycle, because it's not complicated. You just have to read through and make sure that you proceed in the right order and draw the right transformations. Okay, so here we have a 3-stroke heat engine, and we're told that an engine operates under the following cycle. It's going to start with an isobaric expansion, meaning volume increases at constant pressure, followed by an isochoric cooling. So then, well, temperature's got to drop at constant volume, so pressure's going to drop with it. Right? If V is constant, if T drops, P drops by the ideal gas law. And then from C to A, we have an isothermal compression. Okay, and we know that we have capital N moles of oxygen, which is a diatomic gas. Okay, so we're told diatomic gas, and the thermodynamic cycle described by the gas is entirely defined by the pressures PA, PC, and VA. And assume that PC is PA over 2, and therefore give all answers in terms of NR, PA, and VA. So first let's sketch this thing, and then let's determine the efficiency of the engine, and like that we can talk about what the efficiency of a cycle is. All right, so we're going to have a PV diagram like this. I'm going to be starting, let's say, up here with a pressure PA at point A. I know that the gas is going to expand at constant pressure, so the volume will increase at constant pressure like this. We are going to go from VA here to VB. We don't yet know what VB is, but probably we can figure that out. And then we know that we're going to drop at constant volume. Now, to drop temperature, you got to go down like this, right? Because temperature increases this way. So if you're stuck at constant volume, the only way you drop temperature is if you do this. And then we're going to reach a point here where we have a pressure, this is point C. PC, we're told, is PA over 2. Again, this is not to scale. And then we're going to have an isothermal compression all the way from C to A. Now I'm going to draw it like this, but just so we're clear, this is isothermal. And an adiabatic compression would look similar. It would be steeper, but if I don't have an adiabatic process to compare against, I don't know how steep to draw this. So it's okay. You tell me it's isothermal. This is roughly what it looks like. And I'll just keep in mind that it's isothermal when it comes to computing work and heat. Okay, so we have this. This is our cycle. We have a diatomic gas once again, meaning that we have gamma is 1.4, Cp is 7/2 of R, and Cv is 5/2 of R. Okay, and we need to determine, having drawn the cycle, all the unknown pressures, volumes, and temperatures. Now we only don't know one volume, right? Because we're told that PC is PA over 2. So we need to find VB. All right, to find VB, we're going to argue that C to A is isothermal. And if it's isothermal, then TA is equal to TC. And yes, TA is equal to TC, that's right. Okay, now that means that TA is equal to TC. Well, that means that PA VA over NR, come on, NR, there we go, is equal to PCVC over NR. Of course, NR goes away, and we get PA VA is equal to PC. Well, VC, but okay, VB is VC. I mean, B to C is constant volume. So let's see what we get. We're going to find that VB is PA VA divided by PC. And PC is PA over 2. So it's PA VA divided by PA over 2, and so it's 2 VA. Makes sense. For an isothermal process, if you have the pressure, you double the volume. So this is 2 VA. Okay, let's make a copy of this. We're going to carry it along with us for the rest of the problem so that we don't have to scroll back up and down all the time. And let's figure out the efficiency of this cycle. Now, efficiency, the problem is nice. It reminds you what efficiency is. Efficiency is the work that is done by the gas over the whole cycle. So it's the net work, or sometimes we just call it work cycle. I think that makes maybe a little bit more sense. So it's the sum of the work around the whole cycle. Work from A to B plus work from B to C plus work from C to A, divided by Q in. Okay? Now, like I just said, this is work AB plus work BC plus work from C to A. So we're going to compute all three. We're going to add them together. That's going to be work cycle. Q in, on the other hand, is the sum of the positive Q's, which means that we're going to find QAB, QBC, QCA. We're going to keep only the Q's that are positive and add them together. Now, if you're really good at thermo, you can look at the cycle and know exactly which Q is positive or negative and just say, well, I only need to know, I don't know, QAB, for example, is the only one I need to know. QBC is going to be negative and QCA is going to be negative. If you're that good, great. But we're going to assume that we're not that good, and we're just going to kind of, like a knuckle dragger, we're going to compute all the works and we'll add them together, and then compute all the Q's and we'll pick out the positive ones and we'll add them together at the end. Okay, but that's what the efficiency is, and effectively it's what you get divided by what you pay. Right? The whole point of an engine is to produce useful work. So maybe you rotate a shaft or something. How much do you have to pay? Well, you have to pay Q in. In other words, you have to supply heat to the engine so that it uses some of it to generate work. What it can't use is just going to be waste heat, but some of it will be transformed into work. And the ratio of the two is going to be your efficiency. Okay, so here we go. Work from A to B. Work from A to B, well, A to B is a process at constant pressure. It's isobaric, so it's going to be PA or PB, doesn't matter, they're the same, times delta V, VB, minus VA. And this is going to be equal to, therefore, PA times 2VA minus VA. And that's just going to be PA VA. Okay, now remember, the problem wants me to give all my answers in terms of PA, VA, and NR. And in general, you can always get everything in terms of pressure and volume. You don't need to involve temperature. Or if temperature is involved, there's a way to get rid of it through the gas law. Okay, well that's a positive amount of work, but that makes sense. A to B is an expansion, and the work done by the gas when it expands is positive. Work from B to C, simply going to be 0 because it's isochoric. Volume doesn't change, means no work done by the gas. And then work from C to A, well, it's an isothermal process, so I'm going to go look at my chart, and I'm going to see that, or my table, and it's going to be NR, TA or TC, it doesn't matter, they're the same. Natural log of V final, which is going to be VA,
over V initial, which is going to be VB or VC, they're the same. And so nRTA by the ideal gas law is PAVA. Natural log of VA over 2 VA, which is natural log of a half, which is minus natural log of 2. That makes sense. Negative work done by the gas because it's a compression, so I expect the work done by the gas to be negative. Okay, so that's work for each process. I'm going to add these all together. That is going to give me work cycle. Work cycle is going to be PAVA times, or minus rather, PAVA times natural log of 2. Just leave it like that, but probably it is too tempting not to. I would factor out PAVA. Okay, but this is a positive quantity, right? As expected, an engine should produce work, so the net work over the cycle should be positive. Okay, so that's for work. Let's now do the same thing and find Q for each process. And we're going to, once we've done that, we're only going to keep the positive Q's and we're going to add them together to get Qn. All right, now QAB is what? Well, A to B is an isobaric process. So QAB is going to be number of moles, capital N in this case, Cp delta T, which is Tb minus Ta. This is going to be 7 halves of R for Cp, so 7 halves NR Tb minus Ta. And I want everything in terms of PA and VA, so I'm going to absorb NRTB, or NR into the parentheses. I'm going to get NRTB minus NRTA by the ideal gas law. That's going to be PB VB minus PA VA, and that's going to be 7 halves. PB is equal to PA, VB is 2VA, minus PA VA. And so this is going to be 7 halves of PA VA, which is a positive amount of heat. I want to keep that in mind because at the end I'm only going to add together the positive amounts of heat. Okay, then Q from B to C. B to C is an isochoric transformation, constant volume, so it's NCV TC minus TB. And we're going to have the same kind of gymnastics. So, right, so CV is 5 halves of R, so this is 5 halves NR TC minus TB. Okay, so we can go a little faster here. You showed your work in the previous step. Okay, we know what's going to happen. We're going to get NRTC, that's PCVC, NRTB, that's PVVB. So this is going to be 5 halves of PCVC minus PBVB. Okay, now this is going to be 5 halves. Now PC is PA over 2, and VC is 2VA, minus PBVB, well, that's PA times 2 VA. Okay, so it's PAVA minus 2 PAVA. This is minus 5 halves of PAVA. That's a negative amount of heat. It is lost by the gas. I don't care about that. I only care about how much did I have to put in because I want to figure out how much of that became work. So I didn't know that before. That's fine. Now I know. And I'm not going to include QBC in the QN calculation. And so here I'm going to get, for the final step, Q from C to A. It's isothermal, it's not adiabatic, so it's not 0, okay? But if it's isothermal, then Q from C to A is also work from C to A, which we just computed, and is minus PA VA natural log of 2. That's also negative, so I'm losing heat there too. Don't care about that. I only care about positive Q's. So QN is just going to be QAB, which is 7/2 of PAVA. All right? And then the efficiency of the cycle is easy to compute, especially since they actually gave you the formula here, which, by the way, they don't have to do, but fine. I mean, if you're going to give me the formula, sure, I'll use it. And the efficiency is going to be the work done by the gas over the cycle divided by Qn. That is going to be PA VA 1 minus ln of 2 divided by 7/2 of PAVA. That is going to be 2 times 1 minus ln of 2 divided by 7. All right. There we go. That is my efficiency. Can't really do better than that, not without a calculator, but this is good enough. So, pretty classic question, and you can see how it's easy to write a cycle problem, right? Just put a cycle together. We tell you to find everything. Work, Q, compute efficiency. It tests everything in one fell swoop. It's pretty nice. So a slightly higher probability that you're going to get a cycle on the final rather than just a thermal problem like I did before, or even rather than a calorimetry problem, just because they're easy to deal with and they test a lot of formulas. But once again, and I know I spent the whole first part of this live stream saying this, it is a lot easier to do thermo by just saying adiabatic means this, then work is equal to that. Isochoric means this, then heat is equal to that, and boom, boom, boom. As opposed to trying to conceptually reason what happens to, the gas when heat comes in, but it can't expand or whatever. It's like, that's a lot harder. So thermo is actually very straightforward. At least the thermo that we teach and what we expect you to know is very straightforward if you know your formulas, but you have to make sure that you know them and you know when they apply. But if you're willing to do that, I think you'll find that thermo is a nice way to end Physics 8A because it's actually, it's what you do last, and so you could argue it's the least amount of time you have to learn it, but at the same time, it's more plug and chug than anything else, so there's not that much to wrap your head around. All right, well, with that said, thank you all for watching this semester. Appreciate it. I always enjoy doing this. I've taught 8A for longer than I'm willing to admit, but never got bored with it, and always found it interesting, and typically I like the students a lot. 8A students are cool. For the most part, you don't like physics, and I know that, and but you're willing to learn, and so I'm willing to teach you, and it's a good win-win. So thanks for watching. Thanks for the feedback. It's always interesting to hear what you have to say. Have a few ideas moving forward about how to maybe organize this a little differently, or what could be done, and how often to make videos and whatever. But I'll think about that over winter break and see how I incorporate it moving forward. But thanks again. Best of luck. You're almost there. You've never been this close to the end, as my physics teacher used to say, which of course is always true if you think about the statement. You can say it any time and it's true, which of course all piss us off to no end, but it is the truth that it's around the corner. You're almost done. If you only have to take 8A, then you're done forever. If you have to take 8B, well, we'll just cross that bridge when we get there.
Obviously also live stream 8B, because just like 8A, I find it thoroughly enjoyable. So thanks again. Best of luck with the final. I hope it goes well. Show your work, box your answers, you know the drill. Just do the best you can, and have a great break, because it is deserved every time. So with that, happy holidays, and I will see you next semester. Take care.